Welcome back to the Tuesday section. Just to remind you that if you haven't registered yet, you can go to the secretary room at 208 and register there. And if you have any questions, you can ask me, or Christian, or Mateus, or Gugu, who might arrive here in 5 minutes. Okay? So it is a pleasure to introduce Yoshiharu Kohayakawa from the University of São Paulo. And today he's going to speak about the number of BH sets of a given cardinality.
Yuri, thank you very much for the introduction. Thank you very much to the organizers for this opportunity to speak in this workshop. It's not so often that I'm able to address specialists in several different areas, so it's a great pleasure for me to give this talk. Right, so I'll talk about BH sets. So I should start with the definition of BH sets and Sidon sets, although I imagine this is quite well known. So let's start with the set A of natural numbers, and H is some fixed positive integer, at least 2. Now, this set A is called a BH set if all the H-wise sums of the members of A are distinct. So if I compute these sums A1 plus A2 AH with all of these AIs in the set A, H of them, right? Let's put them in increasing order so that, well, that's well defined. The order is well defined. I require that all of these things are distinct. So that's a BH set. If the set A has this property, then we say the set A is a BH set. In the case H equals 2, this is called a B2 set. And this is often called a Sidon set as well. Okay. So the aim of this talk is the following. I plan to talk about some counting problems. I would like to know how many BH sets there are. We'll have one parameter, this parameter n. So the sets will be taken from the first n positive integers. H is fixed, and I'm interested in asymptotic results, so n tends to infinity. Okay, this is kind of a combinatorial talk. The main method that we will use has to do with graphs. So we will use as a basic tool a certain enumeration result for independent sets in graphs. It's kind of not quite true that you can do everything by using this lemma, but certainly this lemma is the workhorse of what we do. But there are lots of things that you have to do to arrive at appropriate graphs to which to apply this counting lemma. Okay, so there will be some graphs later on. All of what I'm doing, or all I'm talking about, is joint work with Domingos de la Monica Jr. from Sao Paulo, Sanjun Lee from Seoul, Wojciech Rodl from Atlanta, and Wojciech Samoti from Tel Aviv. Okay, so let me start with an extremal problem associated to BH sets. So the extremal problem is as follows. I will use this notation often, so brackets n is the first n positive integers. I'm interested in BH sets A, which are contained in brackets n, and I want to know how big they can be. So I want to know this extremal function fh of n, maximal size of such a BH set A. So I'm interested in this function. This is the extremal problem I'm interested in. So when h equals 2, this is actually a question that was posed by Sidon in the 30s. So it's a well-known problem. So let's kind of to have some feeling about this problem. Let's try a simple argument. By definition, if I have a set A, which is a BH set, all these sums, A1 plus A2 and so on up to AH, are distinct. Of course, these sums are all at most H times n, because the A's are at most n. So you can write this inequality here, the right-hand inequality. So size of A choose H is how many H sets you can choose. Since you allow repetition of the AIs, maybe you have to add this H minus 1. But basically, this is A choose, size of A choose H. all these sums have to be different, and they all live in the first hn positive integers, so you have this inequality on the right. Well, this binomial coefficient is at least this thing, this ratio, roughly a divided by h to the h. So you kind of compute, and you get that the size of a is at most n to the 1 over h with some coefficient ch. Okay, so this means that this extremal function is at most some constant times n to the 1 over h with some constant ch. So for instance, 2h for this constant ch will do. Okay, so this function is actually quite small. It's definitely sublinear. It's n to the 1 over h. Okay, to be more precise, okay, no, also there was an upper bound, so let's talk about lower bounds. You can do some algebraic constructions to prove that this fh of n is of order n to the 1 over h. It's something like 1 plus, well, it's about 1 times n to the 1 over h. This is some construction by Bose and Chawla in the 60s. Okay, so the lower bound is n to the 1 over h, and from above is ch n to the 1 over h. In the case h equals 2, so Sidon sets, you know better, you know the coefficient. The coefficient is kind of 1. It's n to the 1/2. So f2 of n is asymptotic to n to the 1/2 with coefficient 1. But if you consider larger h, more than 3 or more, then you basically know the order of magnitude, n to the 1 over h. We just proved it. Well, we said this. But we don't know the coefficient, ch, in general, for large h. Okay? Now, this was the extremal problem associated to BH sets. Now, let me talk about the counting problem. This is the main problem I will be talking about. So the question is as follows. Again, you consider BH sets contained in brackets n, and now I want to know how many of them there are. So, and the number I'm denoting by this ZNH. The total number of such sets in brackets n. Okay. Actually, the question of estimating or determining or estimating this quantity Zn of h was posed by Cameron and Erdős. In the specific case, h equals 2, because that was already interesting. And let me show you. So this is the paper. So on the number of sets of integers with various properties. So this B2 property was just one of many that they considered. So they say, so let me read. So a number of questions in combinatoric number theory consider the maximum number of integers in brackets n satisfying some constraint. For example, containing no solution to a specific equation. Okay, so this, it's our purpose here to examine a related question, which is the number of subsets satisfying the same constraint. So this is the associated counting problem. So they kind of, still in the introduction, they say, well, if I have a family curly A of subsets of brackets n, which is closed under taking subsets, then you can write down this, these inequalities, so this star. If you know that curly A contains a member of m elements, then clearly if you take this member of curly A and take all subsets, you get members of curly A because it's closed under subsets. So you have this lower bound. Size of the family A is at least 2 to the m. And on the other hand, if m is the maximal size of members of A, the sum of these binomial coefficients is clearly an upper bound for the size of this curly A. Okay, very good. And now, but they still, so they carry on and say, if you have better estimates for the size of A, maybe you can say something about the structure of A. So for instance, if the size of this family A is closer to the lower bound in star, so 2 to the m, maybe you can say that there are just a few members of A, of this family, and actually curly A is just the downset generated by these A's. So you just take the subsets of some given kind of well-structured sets. Maybe such a thing is true if you are close to the lower bound. So it's quite interesting to try and prove that the families A are close to the lower bound in size. So they talk then about Sidon sets. So for Sidon sets, we know that the size is root n. So the number of Sidon sets is between 2 to the root n and n to the root n, with 1 plus little 1 in the exponent. And then, so here they thought a little bit about this, and they could prove that in the case of Sidon sets, actually the lower bound is not quite right. So the lim sup of how many Sidon sets you have in brackets n divided by this obvious lower bound actually tends to infinity. So, okay, so there was Cameron Erdős in late 80s, early 90s. Yeah, the paper was published in 1990. So let's now go back to our BH sets. Again, we have the extremal function, fh of n, maximal size of a BH set in brackets n. So again, by this argument about downsets and so on, it's clear that this is a lower bound for the number of BH sets in brackets n. So this is Zn, oh, I'm sorry, this should be Zn h. That is the lower bound for BH sets in brackets n. It's a lower bound. And the upper bound is that sum of binomial coefficients. Given that we do know that fh of n is of order n to the 1 over h, if you just plug this into this star inequalities, you get the following. You get Zn of h is at least 2 to the n to the 1 over h, and 2 raised to n over h log n. So there's a log n difference in the exponent. And well, this is some constant. Okay, yes?
Already for Sidon sets, you have this log n?
Well, if I just use this, yes. Yeah, if I sum these binomial coefficients and kind of just use the fact that they're at most root n, I get this log n. So there's a log n difference in the exponent. Okay, so we were able to prove that actually the lower bound is correct in the following sense. So for every h, so for Sidon sets and BH sets in general, for some constant ch, double prime, the number of such sets is at most 2 to the n to the 1 over h. So this is the lower end of that big range that we had. Okay, so this is the first thing. It would be lovely that from here, or from the proof, you could say a lot of things about the structure of BH sets, or Sidon sets even, but it doesn't, unfortunately, we cannot say so much about that, but we can kind of prove this. And actually can compute more precise bounds, and I'll come to that in a moment. So again, so this number of BH sets is closer to the lower bound of that range that we saw in the Cameron Erdős paper. Good. Okay, so this is the first thing. Let me say something specific about h equals 2. Let me talk about the lower bound for h equals 2. In this case, there's some, well, perhaps a little surprise. Saxton and Thomason proved that the lower bound, the obvious lower bound, was this, right? Was 2 to the f2 of n. So you take one fixed Sidon set, take all subsets. This is the obvious lower bound. And the question is whether it's kind of about, perhaps it's close to this, the number of such sets. But the answer is that it's not true. So there's some coefficient here, bigger than 1, that you can put here. So this is the result of Saxton and Thomason. This is proved by some blow-up construction. It's not particularly difficult, but well, okay. So we know that we cannot have precisely the lower end of that range as the bound for, at least for Sidon sets. Yes, there is some mismatch here. So this is 2. I want to write f2 of n here, right? So I want 2. Since we do not know how much f of hn is in general for general h, you cannot quite write some inequality like this. But anyway, so for Sidon, we do know one can do better than this. Yes. Yes, this is square root. Yeah, so we know this is 1 plus little 1 square root of n. So you know precisely.
So
oh, what did I? Oh, I'm sorry. Yeah, this should be a square root I wanted to write this half raised to, this square root 5 so that you know what numbers this is, and then, but then I forgot the square root n. I'm sorry, this is square root n. Thanks. Okay. Now, so that was something about lower bounds. Let's go back to upper bounds. And I would like, so we were, yes.
So what's your rank? So what's your upper estimate for?
Yeah, our number wasn't so bad. I saw that paper more recently, so I know that number. That number is 55 instead of 1.16. I think ours is 5 or 6. Yeah, right. They were not kind of shooting for very good constant. They had some method which they could apply, and they got 55 out of it. We kind of worked more directly on the problem, and we got this kind of smaller number. Okay. Now, upper bounds, back to upper bounds. And I would like to do this in a more refined way, in the sense that instead of counting the total number of BH sets, I will be interested in the slices. So this was the total number. I'm now interested in this function here, where so there's some extra parameter, new parameter t, and t is the size of the BH set I want. So I want to know how many t element BH sets there are in brackets n. And I want to do this for kind of a range of t. Okay, so the result will be some, well, it will be some number, right? Some function of n and t and h and so on. So that we get some feeling about these numbers, I would like to talk a little bit about actually lower bounds, so that we can kind of understand the numbers somehow. So h is fixed, at least 2. If t is very small, well, very small, if t is at most n to the 1 over 2h minus 1, so a small fraction of n to the 1 over 2h minus 1, it so happens that the number of BH sets of t elements is actually not so different. Well, it's different, but not so different from n choose t. N choose t is this total number, and out of them, 1 minus delta to the t are actually BH sets. And you can specify you can specify delta. So if you tell me what delta you want, there's some epsilon that I put here, so that this inequality here is true for large n. Okay, of course, it's an exponentially smaller fraction. It's an exponentially small fraction of the universe, n choose t, but still, it's something. Okay, and there is some, well, this is true for t, which is at most this. Now, well, this is here just so that you kind of, so that we can compare numbers later. Let me carry on. Now, if t, now let's talk about larger sets, larger BH sets. So t is allowed to go up to the extremal quantity fh of n, so kind of n to the 1 over h. We let t be kind of some small fraction of the maximum possible. Right? If you do that, you can prove the following lower bound. The lower bound is of the form n divided by t to the h raised to t. So here is n divided by t raised to t. This is n divided by t to the h raised to t, and some coefficient here. Okay, so this is the lower bound. So we assert a lot less when t is allowed to be bigger, kind of n to the 1 over h. That's what you can prove. And this is, again, is here just so that we can compare these two numbers. So one is exponentially small in t, and the other one is exponentially in t with the base of the form 1 over t to the h minus 1. So it's a lot smaller. So something kind of happens at this point here, n to the 1 over 2h minus 1. Up to here is quite big, but then... Now, let me try to give you an idea of how these numbers work or what they are. So for that, I will try to give some rough sketch of proof of these two lower bounds. Okay, so this 3, 1 is when t is very small. Okay, when t is very small, okay, we want to bound the number of BH sets. We use the following remark. let m, so m is kind of the same number, the same sort of number as t, for which we want to bound Zn ht. For such an m, let's consider a random m-element subset of brackets n. So I have brackets n, and I take a random subset with m elements, all of them equiprobable, uniform distribution. Now, if you do some simple expectation calculation, you see that the number of conflicts. So for a BH set, I need all the HY sums to be different. And a conflict is if I have two H sets that add up to the same quantity. You can count these conflicts. And the number of conflicts is very small, so that typically a set of m elements for such an m is such that if I take this is my notation for this m element set. A bit weird, but anyway, this is the notation. So I can remove some set t, which is small, which is of smaller order than m, and I can make the set a BH set. It's just this is some simple expectation calculation. You can delete some elements of your random set to make it a BH set. So this means that you generate this m set, random m set. It contains a BH set, which is a kind of about the same size. So that's a way of counting BH sets with t elements. I do the following, right? I take m to be slightly more than t. I want a bound on t. I take m, which is just slightly bigger. I take such a random set, delete, get a t set, which is a BH set. I get many of them. But maybe I get with repetition, right? So maybe this random set gives me some BH set of t elements here. Some other gives me the same. So I have to kind of get rid of this double counting, this multiple counting. And to do that, you just have to divide by this binomial coefficient. And then it turns out that, this is some binomial identity. And then it turns out that you get this lower bound with this very simple method. You get n choose t divided by this, but m is just slightly bigger than t. So this is some exponential in t, but it's not so big. So it's kind of, you get that. OK, so this is why when t is small, namely t is kind of like that, n to the 1 over 2h minus 1, then most sets, or many sets, are BH. OK, so this was the first range. Now this is the second range. So the second range, so I want to prove, again, a lower bound for this quantity number of BH sets with t elements with this t, right? So it's now much bigger, allowed to be much bigger. So we use now the different method. We do the following. Yes. Oh, yeah, so this was, right. Here, I wanted to count t sets. And the procedure was the following. I have m, which is t plus some little bit. This is the mth layer. Here's the tth layer. And a typical set, which I called this. I said that a typical set here has the property, so with some small exception, has the property that I can find a t element subset, which is BH. This is BH. And I want to know how many I have here. This procedure, unfortunately, may generate kind of repeated the same set many times. And I just divided by this. And the randomness was just to say that typically, so with probability, so here I have, this would be everything. And I don't know, with probability 1 minus epsilon, so the exceptional set is of size at most epsilon times nm. Maybe I don't have this property that I can find a BH set of size t inside it, so those I discard. So, but for most of them, I can do this. And so that was the only place where randomness was used. OK. So now we want a different bound. We want a bound in a different range, so we allow t to be bigger. So t can be like kind of close to n to the 1 over h. So the procedure now is the following. Here is brackets n. We split brackets n, and I'm interested in this quantity. So a BH set with T elements. You do something pretty natural. You split brackets n into consecutive intervals, T of h of them, all of the same size. So each has size n divided by T to the h. Okay, now we use the fact that we know how much f of h of th is. So if you think of these th as ground set and you want to find a BH set inside it, you can select some number of indices or intervals so that this is a BH set with cardinality. I call T prime here to be more precise, but T prime and T are kind of about the same. So let me ignore this difference. So you can find some indices forming a BH set. So you can select some intervals. Okay, now you do this. You take some initial segment here of these intervals. These are the J's here. These are the J's. And you choose here to be a fraction of something like 1 over h or 1 over 2h of these intervals. Those are the J's. Okay. Now you just do some simple, well, then there is a simple remark, namely, if you pick any element here, and any element here, and so on, so you can do it for the T blue guys, or T yellow guys, you get a BH set in brackets n. It's just, well, so the elements come from intervals forming a BH set. Then if you select any member here, any member here, any member, and so on, you get a BH set. So this means, but how much? Well, I have T places to choose from, and each lets me have, well, n over 2h or 3h T to the h. Remember, all these intervals had size n over T to the h. I divided by 2h or 3h. Maybe I changed my mind at some point. So you get this lower bound of the form n divided by T to the h raised to the T prime, because I'm being precise, a little bit more precise there. T prime and T are about the same. So this completes the proof. So it's also some kind of a blow-up construction using the fact that from these T to the h intervals, I can extract a BH set with T elements. Okay, so this gives us some idea of these numbers, what these numbers are. So again, the lower bounds were these. 1 minus delta to the T times the universe. And here, this kind of coefficient, right? 1 over T to the h minus 1 to the T of the universe, kind of. And the result is that actually you do have this very different behavior as T grows. So the precise statement is as follows. I'm interested when T is just above the threshold we had in the previous slide. So let me go back. So this is the kind of apparently interesting threshold. When you are above it by a little bit, by epsilon in the exponent, then you actually have a bound of the form n divided by t to the h to the tth power. And again, the lower bound was like this, n to the t to the h raised to t. Okay, right. So this is valid for every t. The lower bound is valid for every t, as long as there are BH sets. And the upper bound is this. They're very close, quite close, but of course there's some cheating because there's some epsilon here in the exponent of t, h minus epsilon, although epsilon can be arbitrarily small, but they're kind of close. So one might say that the conclusion is that if you are just above the threshold of n to the 1 over 2h minus 1, you have this kind of, you have this bound. So it's sharp up to this t to the little ot factor. And so this contrasts quite a bit with what happens below this threshold for t. So if t is smaller, then the kind of, so you have this 1 minus little o1 to the t fraction of the whole universe being BH. So one way of saying this is that the probability, so now take you have brackets n, and you want to select a random t set. You want to know what t sets look like. So take a random one. Then the probability that this random guy that you picked is a BH set, kind of has a dramatic change at around this n to the 1 over 2h minus 1. As I wrote this, or it's actually written in the paper maybe, it's really a dramatic change. So the probability that you are random, you are BH, goes from just slightly sub-exponential, maybe, exponential, to something much smaller. But as I was writing this, I kind of thought that, to me, this is really dramatic. But then you can deduce what kind of boring life I have if I find this dramatic. But anyway, so I think this is dramatic. So you go from this probability to this probability as you increase t, right? Okay, so there's some change of behavior. And now, so I would like to say, so I used this Cameron-Erdős paper to try and motivate this problem. We were actually looking at something a bit different. So it was some probabilistic problem. There is kind of a branch, some results in this direction in several kind of instances. This is more than acquired taste. I think this is kind of interesting. But anyway, so let me say just briefly about what we can deduce from this result. So over the problem that we're trying to solve when we're looking at this. So again, I'm interested in typical subsets of typical subsets of brackets n with cardinality m. This is what I called brackets n m previously. So I pick one at random. And now I ask, how big a BH set can we find inside this random set? Okay, so I have n. I have some other number m. I select an m element subset of brackets n. And inside this set, I would like to find a large BH set. And I will use this notation fh and the set to say how big the set is, BH set is. Okay, this is a random variable because what I put inside here, this brackets n, m is a random object. Well, of course, if I take n equal to m, I have a fhn. And we said this before, this appeared before. When m is kind of small, this n to the 1 over 2h minus 1, essentially everything, you can kind of delete a little bit and get a BH set inside your random set. This is what we used before. And you can ask, so, okay, what happens for larger m? And it turns out that if you are above this threshold that we have seen, n to the 1 over 2h minus 1, the picture changes completely. The BH set, largest BH set you can find inside the random set is actually of order little o m. So you have m, but only a small fraction of it can be put into a BH set in the typical random case. And this follows from results of Schacht and Collin and Gauss. So they have a very general, different but general method of approaching such problems, such probabilistic problems. And it follows from their result that this function does change dramatically at n to the 1 over 2h minus 1. Actually, we can say more. Because of our bounds, we can say more. And to describe the result, let me do the following. So here's the theorem, or the beginning of the theorem. And in the theorem, there is some piecewise linear function, this guy. So it's linear at the beginning, and then it's flat, it's constant. And then it's a over h is linear again, with coefficient 1 over h. Let me show you. This is the graph. So there's some linear. I need this BHA function of a. I need this piecewise linear function to describe the theorem. Okay, so here's BHA. And so what is the theorem? The theorem is as follows. I'm interested in random sets brackets n, m. And now let's parameterize m as n raised to some power a. And a is any number between 0 and 1. So I have a random set brackets n, m, and m is n to the a. What is the largest BH set inside of this set? The theorem says that it's of the form n to the BHA, so it's some other power of n. And the power is given by this piecewise linear function. So again, so on the x-axis you have a. So you're talking about a random set of size n to the a. And inside it you want to find a BH set. So for instance, if a is 1, you get 1 over h. The function, this b, is 1 over h, right? At the beginning, it's kind of the same. A and b are the same. But then at some point, namely 1 over 2h minus 1, you kind of go to a very different regime in which the largest BH set kind of doesn't change as you increase a. The random set increases, but the BH set stays the same. And then at h over 2h minus 1, it picks up again and kind of grows linearly and hits 1 over h at 1, which it should, given that in the deterministic case, we know this is the bound. Okay, so we find this behavior kind of interesting. And this was the original motivation for this. But now I will try to say a few words about the proof. So I'd like to count BH sets of a given size, and I'd like to say what kind of approach we use. Okay, we are interested in these quantities, number of BH sets with T elements, where T is at least this. Good. Proof strategy. We start with some set S of appropriate size. I will soon say something about the size of this set. This is some seed set. That's how you start to grow your BH set. And we want to know in how many ways you can grow it. Right. So this says precisely what I said now. So we want to investigate in how many ways we can add S prime to S so that S union S prime is a BH set. And my aim is to count T element BH set. So I want to add S prime so that I get a set of size T at the end. Right. This is very simplified, but this is what we want to do. And I said that S, the seed set, should be of some appropriate size. We are talking about sets of this T and at least n to the 1 over 2h minus 1 plus a little bit. So I can take S to be of size more than n to the 1 over 2h minus 1. So this is my initial set. I will not try to control it in any way, at least now. So I kind of think, well, I could have anything for this seed set S. But it's kind of some size. Okay. Now, I want to add S prime to S and keep it a BH set. Oh, I'm sorry. I started with a BH set S, right? So I started with a BH set S. I know no bound for how many I have. Maybe n choose size of S. But I start with a BH set. And now I add some S prime, and I want to keep it a BH set. Now, suppose that I have these elements A1 and B1 in these equations here. So these are all members of the seed set S, the original set. And consider this equation. So I have X and Y. Clearly, if I have X0 and Y0 outside S, and I want to put X0 and I want to put X0 and Y0, which solve this equation into my set S prime, so I want to add it to S, then it's no good because I get a conflict. Right? So I have A1 up to AH minus 1, B1 up to BH minus 1. That's already there. I cannot put both X and Y or X0 and Y0 solving this equation into S prime. Okay, if I put X in S prime, then we cannot put Y in S prime or X0 and Y0, sorry. Okay, so we focus our attention on this equation. Now, here's the heuristic to understand some of these numbers. I have 2H minus 2 choices for A1, A1, A2, B1, B2, and so on. So 2H minus 2 choices. And my set, and they come from the set S, seed set, which has little s elements. Maybe I didn't say it has little s elements, but so little s elements. So that's how much I have of choice for the AIs and BIs. Okay, once I put X0, how many Y's do I forbid because of this conflict? Well, X0 is fixed. I vary A, vary B. If I'm lucky, all of them forbid different things. So I forbid S to the 2H minus 2 things, elements for Y. Now, I want to add S prime to get a set of size T. So I have to add not only one X0, but many. How many do I have to add? Well, I have to add T minus S, well, whatever I need still, right? And I choose T much bigger than S. We have room for that because T is big and S is big, but not so big. So I actually add at least S more elements, S or more, little s or more. So this gives me S, little s raised to 2H minus 1 elements forbidden. Okay, and S, this little s or size of S, is n to the 1 over 2H minus 1. So I got one extra power here of S because I have many X0s. So I kind of essentially forbid everything. So this is kind of how the numbers work. And the point is to prove that, in fact, kind of you can make this work, right? Because you have lots of repetition. The same Y could be forbidden by different X0s and different choices of A's and B's and so on. But this gives you the number. Okay. So there's this game. So if you put X0 in S prime, it forbids Y0, where X0 and Y0 solve that conflict equation. Now you can formulate that as a problem in graphs, and here is the you formulate that as a problem in graphs, and then we use well, you have to define the graph, and then we apply some counting lemma for independent sets. And when you do this, when you do H equals 2, actually, it's fairly straightforward, or yeah, it's fairly straightforward. So you need one more step after the lemma. For H equals 3, it becomes more difficult, and general H is actually really quite messy. Okay, so let me talk now about this graph lemma. So let G be a graph. I say that a set I of vertices of this graph is independent or stable if there is no edge with both endpoints in this set. So if I restrict my attention to this set of vertices, I see absolutely no edge inside. There are edges joining this to the remainder of the graph, but not inside. This is an independent set. or stable set. And we're interested in counting them. So I'm interested in this extremal function I of g of s, number of independent sets in the graph G with s elements. We want to bound this, and we want to bound this from above. Okay, so here's the lemma, the independent sets counting lemma. Let's start with the graph G, and now I have big N for the number of vertices of the graph. And now I need some numerical parameters, and the parameters are beta, Q, and beta. Let's not look at this so much right now. Let's look at this condition, which is much more combinatorial and perhaps easier to understand. I have this graph G, and I'm interested in sets A of vertices of G, so subset of vertices. So here is G, and I look at A, subset of vertices. And also, I'm supposed to look at A, which is not so small. So this is at least some size A. Then the condition on the graph is that I see many edges. Namely, well, A choose 2. Here is how many edges I could have in this graph, in this place, in this set. And I have a beta fraction of it. So one might say this is beta dense. Density at least beta. Okay, this is the condition you want on your graph. You want it to be true that if you take sets of reasonable size, you see many edges. You see at least beta in density. Okay, then the number of independent sets you have in this graph G with Q plus M elements, so some given number of elements, is given by this bound. N choose Q times R choose M. Right, okay, let me try just to explain what this is, and I'm running out of time, so let me just try to explain what this number is. Previously, so Kleitman and Winston, this method, this idea was used by Kleitman and Winston. They invented some algorithm to prove this, but it has been used since in several different contexts. And it seems to be a lemma that is it's very simple to prove, but seems to be quite powerful. So let me try to explain this quantity here. You do the following. You want to prove this bound, let's say. And you kind of think, again, there is some seed set Q here. This is some, sorry. I'm counting independent sets. So maybe here's an independent set. And I want to count how many of these guys I have. Actually, you look at some seed set Q, some small independent set. And if the numbers are so, this picture does not quite right. But if the numbers are so that, right, I'm sorry. You start with this seed set Q. And this N choose Q is how many seed sets you have. Now, once you put this seed set Q, what happens is that because of this density condition, you prove that these points forbid lots of other points, vertices in the graph. And actually, you show that the remainder of this independent set must be contained in some set of size at most R. Very roughly speaking, you see this graph. Here we are talking about density beta. So on average, every vertex has beta times n vertices. And if you're lucky, all of these vertices inside the seed set forbid something like beta fraction of the remainder. So if you do it Q times, the kind of available space shrinks Q times by a factor of 1 minus beta. So you get this 1 minus beta raised to Q. Which is this e to the minus beta q, which shows up here. So the whole game is to kind of to show that if you take you can select a seed set in such a graph so that maybe the beginning is completely arbitrary, but the remainder of your independent set is restricted to a set of size R. and then you, yeah, okay. So that's kind of the bound. I'm sorry, I ran out of time. I will just do the following to this. Right, so here's a conjecture. Well, let's put it as a conjecture. We have some minus epsilon here for the number of such BH sets. And this epsilon is really necessary in the proof. Maybe the proof is too messy. Maybe there is a much better way of doing this. And then maybe you can get a much cleaner bound like this. And also, we had an epsilon here in the exponent for the bound on T. We need T to be at least this, but with plus epsilon on top. Maybe that's not necessary. Maybe there's a much better approach to this. It's not clear. This connects to the second remark. So maybe, so I didn't say anything about something called the hypergraph container lemmas, which seem to be a very nice uniform way of treating problems of this kind, counting problems of this kind. Actually, this is let's say, a hypergraph version of this independent sets counting lemma, which I just spoke about for a few minutes now. And if you're interested in this graph case, if you want a nice introduction to this, I recommend this survey by Wojtek Samoti, which appeared recently. So he shows several applications of this in combinatorial problems and problems in combinatorial number theory also. Yes, so I overran, so I should stop. Thank you very much.